In our study of differential equations so far, we've looked at one model of growth, and that's exponential growth, which is based on this assumption that the change in population is directly proportional to the population at a certain moment in time. And we know that if we solve that differential equation, we come up with this exponential function for exponential growth if k is positive and exponential decay if it's negative. Growth graph, decay graph. The problem with exponential growth is that population may be increasing, but the chances are it won't be able to continue increasing forever, which is what our model of growth says will happen. And so what we really need is a more realistic model of growth to account for the fact that although populations often start off increasing exponentially, there's a point at which it starts to level off towards some maximum population, which we call the carrying capacity. And this is what we call logistic growth. Population is restricted from growing past a certain point for various environmental and economic factors, and so it starts to level off and approach some fixed carrying capacity. The graph I've drawn here is a situation when our population is smaller than our carrying capacity and grows to approach the carrying capacity. Another scenario is when perhaps you're stocking a lake with fish or whatever, and if you put too many fish into that lake, if you have an overpopulation and the lake can only support a certain amount, the population is going to decline until it approaches the carrying capacity. So here's a negative growth situation when our population is greater than our carrying capacity. And I guess the third situation is that when your population is at your carrying capacity, it will remain constant because that population can be supported. So the idea of logistic growth, just to summarize, is that our population is restricted by various factors, and there's a maximum population, M, called the carrying capacity, that the environment is capable of sustaining in the long run. And just to summarize, we have three scenarios. If our population is less than our carrying capacity, or in other words, the ratio of P to M is less than 1, then we're going to have a growth situation, and the population is going to grow towards the carrying capacity. If our population is greater than our carrying capacity, then P divided by M will be more than 1, and we'll have a situation of negative growth, declining growth, as our population approaches and declines to our carrying capacity. And if P is equal to M, P over M would be 1, and our rate of growth would be 0. We'd have a constant rate of growth. So what we want to do now is take our understanding of this model and convert it into a mathematical model that will allow us to come up with an equation that reflects this reality. And here's the model we're going to use for logistic growth. The rate of population growth is directly proportional. I'm going to use a capital K here. Directly proportional to the population. Now up to that point, that would just be exponential growth, wouldn't it? But we've got this extra little piece to multiply on, as well as the difference between the carrying capacity and the population. This is our differential equation model for logistic growth. And in a moment, you'll see how it matches what we need it to do from above. I'm going to do a couple things here. I'm going to factor out an M out of this bracket, and I'm going to make my model now look like so. And then I'm going to assign capital K over M to be a different constant, little k. So get your big K and your little k distinguished. Little k times P times 1 minus P over M. And it's this form of the differential equation that I'm going to use most frequently, and you'll see why in a bit. But for now, you want to be able to recognize that either form of this as a differential equation for logistic growth. Let's just talk a little bit about how this differential equation meets the conditions of what we had laid out above. You'll notice that I have ratios for P over M. And I can see that if this is less than 1, then this entire quantity, because P will be a positive amount, it's a population, then dP dt will be positive, and we'll be talking about growth. If P over M was more than 1, then this is all going to come out to a negative quantity, and so dP dt is negative, which means our population is declining. And if P over M is 1, then 1 minus 1 will make this 0. The population change will be 0, and the population will remain stable. So hopefully you can get the sense of how these three conditions are reflected in our differential equation. So we have our differential equation for logistic growth. And what we now do, of course, is we solve our differential equation by separation. Now this process is quite long and drawn out, and what I'm going to do is I'm just going to walk through some of the main points so that you see how it's solved, and then we want to get to the main point, which is the solution at the end. So I'm starting off by factoring 1 over m out of the bracket to give me this. I'm then going to separate my variables, so dp over p times m minus p, and my constants on the right. And then I need to integrate both sides. But integrating on the left is going to require integration by partial fractions. I have 1 over p times m minus p. So this expression on the left has to be broken up using partial fractions. So I've done that. This is equivalent to this fraction plus this fraction, which is equal to the integral of this. And what we will now focus in on is just these two terms moving forward. From here, I'm going to multiply both sides by m, and so I'm left with this. And now I can integrate. ln absolute value p minus, just be careful with this term, there's going to be a u substitution here. M is a constant, remember, p is our variable. There's going to be a negative 1 coming out of our u substitution. So we'll have negative ln absolute m minus p. Subtract logs, divide the parts. We then raise both sides to the base of e, which becomes this. E and ln knock each other off. The absolute value is plus and minus, so I can move my plus and minus as shown. And then e to the c multiplied by my plus and minus is going to become 1 grand constant, c naught. Now I'm going to reciprocate both sides, and so that becomes this. But then over on the right here, the 1 over c naught, I'm going to make another constant c, and e to the kt, that's equivalent to having e to the negative kt in the numerator. Then I break this term up as m over p minus 1. I'm going to add the 1 to the other side. M over p equals 1 plus, and then I'm going to reciprocate both sides and multiply by m, and I come up with my general solution to be as shown. Now I want to take this one step further by finding what my arbitrary c is. So what I'm going to do, we're going to define the population at time 0 to be p naught, and then I can plug that specific information into my equation above. P equals p naught, t equals 0, which makes on the denominator just a constant of c. And then if I solve for c, follow all the work through, I'm going to get c to be the carrying capacity minus the initial population, all divided by the initial population. And so our solution to this differential equation is this equation where our arbitrary constant is as shown. So let's look at some examples of how we would be expected to use this result. We want to solve this differential equation with a given initial condition and then find the limit. So first I'll take my differential equation, and what I'll do is I will factor out 5,000 y, and that will leave me with 1 minus y over 1,000, and I will recognize that I have my differential equation in the form of a logistic differential equation where the carrying capacity is 1,000 and my constant is 5,000. And because I've solved this differential equation to be this, I can substitute these values directly in. But I need my arbitrary constant, but we've calculated that that can be found by using this formula. So that's 1,000 minus my starting population back at the top was given to be 500. And so that's 500 over 500, which is 1. And so my solution is this. We also wanted the limit. As t goes to infinity, we know that this will go to negative infinity, and e to the negative infinity goes towards 0. So towards 0 plus 1 is 1 on the bottom, 1,000 over 1 is 1,000. And our limit is our carrying capacity. Let's look at a practical situation now. A national park is known to be able to support no more than 100 grizzly bears. Okay, that's indicating a carrying capacity of 100 bears. 10 bears are in the park at present, which is our initial population. And the population is modeled according to this differential equation, which I should recognize as a logistic differential equation because I have some constant times p times something minus p. Now, in terms of my solving, what I want to do is I want to get it into this form. In other words, with a 1 in this position, because if I have that, then my constant is the k that I have in my solution. In other words, this matches this. We're also going to need C, and remember that C is the carrying capacity minus the initial population all over the initial population, which let's just calculate that while we're here. That would be 9. So I have M, I have C, but I need to get K, but before I get K I need to reorganize my differential equation so that I have a 1 minus P over M in the bracket. So factoring out my 100, I'm going to get 0.1 P times 1 minus P over 100. You'll notice that my carrying capacity is in the right spot. It's all working out correctly. This is my K. And so, putting all of this together in my solution, my population of bears after t years is my carrying capacity divided by 1 plus 9e to the negative 0.1 t. Let's just take a look at how that looks on the calculator. And we get, of course, a graph that looks like a logistic growth graph. So let's take that equation now and find the time when the growth of the bear population is at its maximum. Now, the one thing I haven't mentioned so far, and that is that the maximum growth rate is that point right there. You got the maximum slope. That always happens at half your carrying capacity. That can be shown using your differential equations. I'm going to save that as an exercise. But your maximum growth rate always occurs at half the carrying capacity. So that, in this case, means that when we have 50 bears. So you can plug 50 into your logistic equation and solve for it algebraically if you want. I'm just going to use my calculator. Population is 50. Get the point of intersection and take the first coordinate. When the time is 21.972 years. In other words, after about 22 years.